Hello, today we are going to go over the Lecture 18 worksheet. There's a request for going over the KSP stuff a little bit more in detail, so I decided just to go ahead and work out this worksheet. If any additional videos on KSP are needed, just let me know. Okay, so within this, with all of these, we're looking at KSP, so the solubility constant. Or solubility product constant. So let's start with the first one. We have 1.38 times 10 to the negative 4 grams of chromium hydroxide added to, or chromium 3 hydroxide specifically, added to 150 liters of water. The KSP of chromium 3 hydroxide is 6.7 times 10 to the negative 31. We want to know if all of it will dissolve. Anytime we ask that, we're basically asking to solve for Q. So we're looking at our reaction quotient. And the reaction quotient works the same as any of the K values that you're representing, so this would be our QSP, if you will. So let's look at this one first. So we've got an amount of chromium hydroxide. We need to convert that into concentration of chromium hydroxide. So 1.38 times 10 to the negative 4 grams of chromium 3 hydroxide. That has a molar mass of 106.041 grams. So when we divide that out, we get 1.30 times 10 to the negative 6 moles of our chromium 3 hydroxide. And then we want to put it in concentration, so we divide by 150 liters. Right, concentration is needed for any of these Ks or Qs, so we get 8.68 times 10 to the negative 9 molar. Now, we're going to set this value right here equal to S, or our molar solubility, and see if that value corresponds to a solubility or not. So in order to determine that, we're going to look at our Q. So let's go ahead and write out our Q expression for chromium 3 hydroxide. So its equilibrium, when it breaks down into ions, we get chromium 3 plus and 3 hydroxides. So our Q expression for this would be concentration of chromium 3 plus times by the concentration of hydroxide cubed. Now, if we have a certain amount of our chromium dissolved, which we call S, solubility, this would be an S, this would be 3S. So we could then put those into our Q expression, and we get Q is equal to S 3S cubed. So Q would be equal to 27S to the 4th. We're then going to place this in for S and solve for Q. So we have 27 times by our 8.68 times 10 to the negative 9 to the 4th. When we multiply that out, we get a value of 1.53 times 10 to the negative 31. And if we compare that to our KSP, we see that Q is less than KSP, and whenever we have that occur, there will be no precipitate. So nothing will precipitate out. Let's try again, but this time we have a concentration of hydroxide in here, which comes from our sodium hydroxide. So when sodium hydroxide dissolves, it completely dissociates into sodium ions, which does nothing, and then hydroxide ions, which will due to the common ion effect, will cause a lower molar solubility in our chromium hydroxide. So we're going to take our sodium hydroxide, so we have our grams of sodium hydroxide. We want to convert that into moles of sodium hydroxide by using our molar mass. Giving us 1.25 times 10 to the negative 5 moles NaOH. And then we want to convert from moles of NaOH into moles of hydroxide. They're a 1-to-1 ratio, giving us 1.25 times 10 to the negative 5 moles of OH minus. And then we'll divide that by our 150 liters, giving us 8.33 times 10 to the negative 8 molar hydroxide ions. That will then go into our Q expression, and we will solve for Q. So now we have our concentration of hydroxide and we have our concentration of chromium, because chromium and chromium hydroxide are in 1-to-1 ratios according to this equation, right? For every 1 chromium hydroxide, we produce 1 chromium 3+. So we'll put that in for chromium 3+. We'll put this in for hydroxide. Along with the contribution up here. So our hydroxide concentration, we're going to take this 8.33 times 10 to the 8 molar, add that to 3 times by 8.68 times 10 to the negative 9 molar. So this is where we multiply 3 because there's a 3 here, and then times it by our solubility because it is 3s. So when we take those, add those together, we get a concentration of 1.09 times 10 to the negative 7 molar hydroxide ions. That, along with our chromium concentration, will all go into our Q expression. So Q will be equal to 8.68 times 10 to the negative 9, and then 1.09 times 10 to the negative 7 cubed. So that's our chromium concentration, our hydroxide concentration, and our Q value would then be 1.13 times 10 to the negative 29. So if we compare that to our KSP, we see that is a larger value, so Q is greater than KSP. So therefore we will have a precipitate. Okay, let's try the next one. Now we're going to look at lead chloride, which has a KSP of 1.7 times 10 to the negative 3. First thing we want to do is we want to calculate use our KSP to calculate our molar solubility. So anytime we're looking at molar solubility, we're solving for S. So we have lead chloride. It's going to break down into lead ions and 2 chlorine ions. Every time we dissolve, however much we dissolve of our lead chloride, we'll dissolve an equal amount of lead, or we'll produce an equal amount of lead ions and 2 times as much chlorine ions due to our stoichiometry. So our KSP in this expression would be equal to lead 2 plus times by Cl minus squared, and we'll put these values in for the concentrations. KSP is equal to S 2S squared, which gives us 4S cubed. We'll then put our KSP actually in here and solve for S, giving us our molar solubility. Remember, S is molar solubility. Okay. When we do that, we get an S equal to 1.62 times 10 to the negative 2 molar. Next thing, it's asked if 5 milliliters of 0.03 molar lead nitrate is mixed with 10 milliliters of 0.015 molar sodium chloride, will a precipitate form? So we've got lead nitrate is a lead source. Sodium chloride is a chlorine source. And since we're adding 2 volumes together, the first thing we want to do is a dilution calculation. So let's look at lead 2 nitrate. So our M1 in this case, so we're doing M1V1 equals M2V2. Our M1 would be 0.0300 molar. Our V1 is 5.00 milliliters. We're going to add it to 10 milliliters, so we'll have a total of 15 milliliters. So our M2 is what we're solving for. Our V2 is 15.0 milliliters. Calculate that out. We get an M2 equal to 1.00 times 10 to the negative 2 molar. And since we have 1-to-1 mole ratio of lead to lead nitrate, that is our concentration of lead nitrate and our concentration of lead ions. Okay, we're going to do the same thing for our sodium chloride. And again, sodium chloride and chlorine are 1-to-1, so this will be equal to our chlorine concentration. So we start out with 0.0150 molar and 10 milliliters of that. And we still have the same final concentration, 15.0 milliliters. Calculate that get out. We get an M2 equal to 1.00 times 10 to the negative 2 molar. And that's of our chlorine ions. And then we have concentration of lead ions, concentration of chlorine ions, and that will go into our KSP expression. But now we're solving for Q because we're trying to see if a precipitate will form, and we're going to compare Q to KSP. So Q is equal to 1.00 times 10 to the negative 2, and then 1.00 times 10 to the negative 2 squared for our chlorine. So this gives us a Q value of 1.00 times 10 to the negative 6, which means our Q is going to be, compared to our KSP, our Q is smaller than our KSP. Therefore, we have no precipitate. We're then going to look at a higher concentration. So same volume, slightly higher concentrations. So we're going to do the same thing. We're going to look at our Pb2+, which is equal to our Pb nitrate. But now we have 0.300 molar, so 1 order of magnitude difference. But all the rest of it is the same. And when we do that, we get a concentration of 1.00 times 10 to the negative 1 molar lead ions. And then for Cl minus, 0.300 molar, or so. 0.150 molar, 10 milliliters, equal to an M2, and 15 milliliters. Calculate that out. We get an M2 equal to 1.00 times 10 to the negative 1 molar chlorine ions. That will then go put into our Q expression. So our lead concentration times by this our chlorine concentration squared gives us a value of 1.00 times 10 to the negative 3. That means our Q is greater than our KSP, therefore we will have a precipitate form. Okay. Let's look on here. Our next one will have precipitate form if 115 milliliters of 0.150 molar tin nitrate is added to 12.5 milliliters of 0.150 molar sodium iodide. Again, we have two volumes added together, so the first thing we're going to do is a dilution calculation. So we're looking at tin iodide. So SNI2. When that dissolves, we get SN2 plus 2I minus. So we're looking at tin concentration and iodine concentration. So our tin 2 nitrate which is equal to our tin concentration as they are 1 to 1. So again, we're doing M1 V1 equals M2 V2. Our M1 in this case is 0.150 molar. Our V1 is 115.0 milliliters. Our V2, we add these two together, so 115.0 plus 12.5 gives us a total volume of, let's see, 127.5 milliliters. Okay. So we're solving for our M2. Our final volume, though, is 127.5 milliliters. Calculate this out. We get an M2 equal to 1.35 times 10 to the negative 1 molar for our tin 2 plus. We're going to do the same thing for sodium. So our sodium iodide gives us our iodide ion concentration. We start out with 0.05 molar, 0.150 molar, and 12.5 milliliters. Solving for M2, final concentration is the same, 127.5. We get an M2 equal to 1.47 times 10 to the negative 2 molar iodine. That will then go into our Q expression. Q is equal to tin concentration times by our iodine concentration squared. So it would be equal to 1.35 times 10 to the negative 1 times by 1.47 times 10 to the negative 2 squared. Multiply that out. We get 2.92 times 10 to the negative 5. We compare that to our KSP up here. We said that Q is less than KSP. So therefore, no precipitate will form. Okay. Next is asking what the maximum concentration of Mg ions that can remain dissolved in a solution that contains ammonia and ammonium chloride. And what I should have written in here is that we're going to ignore complex ion formation. So we're going to ignore that complex ion formation in this case. So we want to figure out, using our KSP, how much magnesium 2+ ions we can fit in when we have this system. If we look, this is ammonia and ammonium chloride, which means that we have a weak base and its conjugate acid, which means we have a buffer. Using this, we can figure out our hydroxide concentration. Okay, so the very first thing we want to do is solve for our hydroxide concentration. So we're going to use Henderson-Hasselbalch. So POH is equal to pKb plus log acid over base. So our POH is equal to negative log 1.77 times 10 to the negative 5. pKb is equal to negative log Kb, which is what I've just put in, as we have our Kb value right here. And then we're going to add that to log of our acid concentration, that right there, and then base concentration, that right there. So 0.228 on the top, 0.786 on the bottom. Calculate this out, we get a POH of 4.21. We can then take 10 to the negative POH, gives us our OH minus concentration. So 10 to the negative 4.21 equals hydroxide concentration. So our hydroxide concentration is equal to 6.10 times 10 to the negative 5. We can then put that into our KSP expression and solve for magnesium concentration. So if we have Mg OH2, as that dissolves, we produce magnesium 2+ ions and 2 hydroxide ions. So our KSP expression in this case would be magnesium 2+ OH minus squared. We're going to take this hydroxide concentration right here and place it into this expression, solve for magnesium 2+. So our KSP up here is 1.2 times 10 to the negative 11. That'll be equal to our magnesium concentration times by our hydroxide concentration, 6.10 times 10 to the negative 5. Solve for this, we get a magnesium concentration of 3.22 times 10 to the negative 3 molar. So anything above this point and a precipitate will form. Okay. Let's try the next one. We have calcium hydroxide. Has a molar solubility of 0.12 molar. We want to first write our balance equations. We've been doing this the entire time, but I'm going to put this into water. So as it breaks down into water, you don't need to add the water into here. That is our expression. If we want to solve for our concentration of calcium ions and hydroxide ions in a saturated solution, we're going to first use our molar solubility. So we have molar solubility of 0.012 molar for calcium hydroxide. Okay. So if we want to convert this into calcium and hydroxide, we're just going to use our balanced equation above. So 1 mole of calcium hydroxide yields 1 mole of calcium ions. So our solubility of our calcium ions in a saturated solution is 0.012 molar. Do the same thing for our hydroxide. Except for this case, we have 2 moles of hydroxide for every 1 mole calcium hydroxide. So we get 0.024 molar hydroxide ions. Okay. We then want to solve for our equilibrium constant expression. So in this case, KSP is equal to calcium 2 plus hydroxide minus squared, and we'll just put these concentrations right here into here. So KSP is equal to 0.012 and then 0.024 squared. And then when we solve for that, we get a value of 6.91 times 10 to the negative 6. Okay, next one, we're going to be relating molar solubility to KSP. So for each of them, we will write out the KSP expression, write out the balanced equation, then our KSP expression in terms of solubility. So first one, we have copper carbonate. When that dissolves, it produces copper 2 plus ions and carbonate ions. For every time whenever we dissolve an amount of copper carbonate, copper 2 carbonate, we produce 1 mole of copper, 1 mole of carbonate. So our KSP, if we put this in, would be equal to S times by S, which gives us S squared. So KSP is equal to S squared. We'll just put the 2.5 times 10 to the negative 10 in for our KSP is equal to S squared, and our S would be then equal to 1.58 times 10 to the negative 5 molar. Same idea for the next one. We have silver sulfate. When it dissolves, we produce 2 silver ions. And 1 sulfate ion. So this would be 2S here, S here. So our KSP is equal to Ag plus squared SO4 2 minus gives us 2S squared S, or 4S cubed. So we put in our KSP, 1.7 times 10 to the negative 5 is equal to 4S cubed, giving us a molar solubility of 1.62 times 10 to the negative 2 molar. Our next one is a little more difficult. We have chromium hydroxide, and we have a buffered solution at a pH of 11.50. Anytime you see a pH, you're almost always looking for either H plus concentration or OH minus concentration. In this case, OH minus is a common ion, so we're looking for OH minus concentration. So if we have pH equal to 11.50, our pOH would equal to 2.50. We can then say 10 to the negative pOH is equal to OH minus. So 10 to the negative 2.50 is equal to 3.16 times 10 to the negative 3 molar. So that is equal to our hydroxide concentration. We will then set up our KSP expression for our chromium hydroxide, chromium 3 hydroxide. So as the chromium 3 hydroxide dissolves, we produce chromium 3 plus ions and 3 hydroxide ions. So S and 3S. Although we don't actually care about the 3S, as we have our hydroxide concentration already. So this would be Cr3 plus OH minus cubed. We have our hydroxide concentration that will go into here. So we have KSP is equal to Cr3 plus times by 3.16 times 10 to the negative 3 cubed. And this is equal to S, or molar solubility. So this whole expression will be S, or put in our KSP, which is 6.7 times 10 to the negative 31. Is equal to S times by 3.16 times 10 to the negative 3 cubed. Then we get an S value, or molar solubility, equal to 2.12 times 10 to the negative 23rd molar. Okay. Next is just a multiple choice question. The result of common ion effect is, if we look at these, sodium ions frequently appear in solutions but do not participate in solubility equilibria. That is true, but that's not what our common ion effect says. Common ions such as sodium don't affect equilibrium constants. True, but still not part of the common ion effect. That the selective precipitation of a metal ion such as silver is promoted by the addition of a counter ion that produces a compound with very low solubility. That's what we're looking at with the common ion effect. Okay, and then the other two are also incorrect. Or correct, but not actually what the common ion effect talks about. Okay, let's try these last two. These last two are dealing with complex ions. So we're looking at how adding ammonia in will affect our concentrations. So we've got copper nitrate. We have 8.5 grams of copper nitrate added to 500 milliliters of 1 molar aqueous ammonia. So first thing to note, copper nitrate will completely dissolve into copper ions. There will be no intact copper nitrate. Okay, so let's convert from grams of copper nitrate into moles of copper nitrate into moles of copper 2+, and then concentration of copper 2+. So here's our copper nitrate. Then I'm going to take this and convert this into moles of copper nitrate by using our molar mass, 187.56 grams, giving us 4.53 times 10 to the negative 2 moles of copper nitrate. And then we divide that by our 0.500 liters, giving us 4.53 times 10 to the negative 2 moles of negative 2 molar copper nitrate. And then for every 1 mole of copper nitrate, we produce 1 mole of copper 2+, giving us oops. Sorry. This is not correct. This should be 9.06 times 10 to the negative 2 molar. And then this gives us 9.06 times 10 to the negative 2 molar copper 2 plus ions. Okay. Now we're going to take this and put this into our equilibrium. So if we have once we place this into a solution of ammonia, it's going to form this complex right here. This is our complex ion. We assume that it completely forms, and then once it forms, it's going to be in an equilibrium process with its copper 2 plus ions and ammonia ions. Okay? Now, that being said, we have our formation constant of our copper ammonia complex ion. To form or to get our equilibrium expression, our equilibrium expression, or equilibrium constant, will be 1 over that Kf because we flipped the equation. So our Keq in this case would be 1 divided by 2.1 times 10 to the 13, which gives us 4.76 times 10 to the negative 14 for our Keq for the dissociation of our complex ion. So we're going to do a Rice table for this, as we would for any equilibrium. So we'd say our initial concentration is equal to this because all of it's going to form our complex ion. And then we're going to kind of ignore, or we're going to assume that there's none of this initially. And we're going to start with 1.00 molar here. As it says in our equation up here. Okay. We're going to do minus x here, plus x, giving us 9.06 times 10 to the negative 2 minus x, x and 1.00 plus x. That will then go into our Keq expression, where Keq is equal to Cu2 plus NH3 to the 4 divided by Cu NH3 for 2 plus, which gives us 4.76 times 10 to the negative 14 is equal to x 1.00 plus x to the 4th divided by 9.06 times 10 to the negative 2 minus x. This value allows us to use a small x approximation. So we get 1x over 9.06 times 10 to the negative 2. And then when we solve for x, we get an x value equal to 4.31 times 10 to the negative 15 molar, and that is equal to our Cu2 plus concentration. Our last question talks about a solution containing silver ions and lead ions. We've got a concentration of both. And with this, we want to find out if sodium iodine is added, which complex will form first, silver iodide or lead iodide. To do this, we're basically going to solve for our iodine concentration, figuring out which iodine concentration is smaller. So we start out with silver iodide. When that dissolves, it produces silver ions and iodine ions. So we'd see that our KSP for this is equal to Ag plus times by I minus. We then are going to put our KSP into here along with our silver concentration. So our KSP is 8.3 times 10 to the negative 17. We have a silver concentration of 2.0 times 10 to the negative 4. And what we're solving for is our iodine concentration. So what iodine concentration are we at our tipping point for precipitation? When we do that, we get an iodine concentration of 4.15 times 10 to the negative 13 molar. Do the same thing for lead iodide. So when lead iodide dissolves, we produce lead ions and iodine ions. So our KSP in this case would be equal to lead 2 plus I minus squared. Our KSP for lead iodide is 7.9 times 10 to the negative 9. This will be equal to our lead concentration of 1.5 times 10 to the negative 3 times by our iodine concentration squared. We then again will solve for I minus, and we'll get a value of 2.29 times 10 to the negative 3 molar. Now, we're going to compare these two values here. We see that this concentration is significantly lower than this concentration, which means that at a iodine concentration of 4.15 times 10 to the negative 13, very low concentration, we will precipitate out our silver iodide. However, a much higher concentration of iodine is required to precipitate out our lead iodide, which means that silver iodide precipitates out first. So at a lower I minus concentration. Okay, that's everything. Hope that made sense. I'll see you guys later.